I'm Francesca Rossi, and I'm reading from Kirkland, Washington. Today I'm going to be reading A Black Hole is Not a Hole by Carolyn, Cinami, DeCristofano, and illustrated by Michael Carroll. And the cool thing about this book is I actually know the author. So it's kind of fun to be able to read a book and you know the person who wrote it. So let's get started. So if a black hole is not a hole, then what is it? Black hole is not a hole. Introduction. Have you heard the news? In outer space, mysterious entities called black holes seem up to no good. From the headlines, you'd think black holes were beasts with endless appetites lying in wait for the next meal. By some reports, they are runaway, out of control predators that feed on galaxies, only to belch and spit out what they don't eat. They lurk in the shadows, mangling stars and gobbling them up. In short, they have a nasty reputation for being monsters gone mad. But you know what? A black hole isn't a monster. It's not even alive. That means it can't lurk, eat, or belch. It has no dark, destructive desires. Of course, you may have already figured this out. But you know what else? A black hole is not a hole. At least, not the kind you can dig in the ground or poke your finger through. You can't just walk along and fall into one. A black hole isn't a hole like that. If a black hole is not a hole, then what in the universe is it? Places with pull. A black hole is a place in space with a powerful pull. Way out beyond where you are right now, beyond the clouds, beyond the moon, beyond Pluto, beyond our solar system, space goes on and on. You could travel for trillions of miles and you'd barely get to the closest star. In another few trillion miles, you might pass another star. Space is that huge. Way out there, trillions, quadrillions, and even more illions of miles away, are special places called black holes. These places in space are special because of their powerful pull on other things. A black hole's pull is the strongest pull in the entire universe. Nothing can outtug a black hole. No army of tow trucks, no convoy of supersized earth haulers, no fleet of giant rocket engines. Not all of them combined. A black hole pulls in nearby dust. It pulls in nearby asteroids. It pulls in nearby stars and even nearby starlight. And no light, stars, asteroids, or dust comes out. Not ever. The superpulling power of a black hole is enough to haul in entire stars. In this artist's image, a black hole reels in glowing gas from a nearby star. The star itself is out of the picture frame. How far out is way out there? Black holes are way out beyond where you are right now, much farther away than the edge of our solar system. To talk about the distance to a black hole, you need a huge number. How huge? Well, in your everyday life, you probably travel only a few miles or kilometers. At most, you might go in tens of miles. Longer trips might be in the hundreds or even thousands of miles. In outer space, these distances would seem smaller than baby steps. Out there, you need to stock up on zeros to describe how far it is from one place to another. From Earth to the Sun, millions of miles or kilometers. From the Sun to the next closest star, tens of trillions of miles or kilometers. From Earth to the nearest black hole, quadrillions of miles or kilometers. Distance across our galaxy, Milky Way, hundreds of quadrillions of miles or kilometers. Distance beyond the observable universe, which may be much smaller than the whole universe, sextillions of millions or kilometers. So just as a little visual representation of that, that's all of these zeros. I know it's hard to see, but this up here is hundreds, and this, which is still hard to see, but that's nanomillions. It's a lot of zeros. And in the universe, enormous distances separate even close neighbors. The Sun and Pluto, for instance, are staggering 3,647,240,000 miles and 5,869,666,000 kilometers apart. Yet that's just a hop, skip, and a jump, astronomically speaking. Sizes and distances in this diagram are not to scale. Here's a little glance at that diagram now. A black hole is like a giant whirlpool. Have you ever pulled out a sink stopper and watched water swirl down the drain? Spirals of water flow toward the center. You've made a small whirlpool. Imagine a bigger whirlpool in a river. Far away, nobody knows it's there. Boats chug and sail along, schools of fish dart by, following their fishy urges. Closer to the whirlpool, it's a different story. A fish swimming near the edge of the whirlpool feels a gentle tug as the current drags it toward the spinning center. No problem. With a little swish, the fish can speed up, giving itself the oomph to swim away. After putting some distance between itself and the whirlpool, the fish no longer feels the current's inward pull. But what if the fish drifted farther in? Closer to the center of the whirlpool, the pull would grow stronger. To escape the whirlpool, the fish would have to swim faster than it had to the edge. Even closer to the middle, if the fish couldn't go much faster, it would find itself swept all the way in, stuck in the swirl, pulled around and around and around. A black hole works something like that, like a whirlpool. Even though a black hole's pull is the strongest in the universe, it's not strong from far away. Galaxies and stardust drifting through space don't get dragged into distant black holes. However, near a black hole, gases and dust and stars encounter its tug. Some things may be hurtling by so fast they won't get pulled into the black hole. Other things might not be as swift. They will be drawn in closer and closer. The tugging force gets stronger and stronger. Close enough, the black hole no longer acts like a whirlpool. The inward pull of a swirling whirlpool gets stronger near its center. The closer a fish or anything else gets to the center, the more speed it needs to get out. Here's a little illustration of a whirlpool and a boat. And it's hard to see, but there's a little fish down there too. Actually, multiple fish. Even though it's like a whirlpool, a black hole is not a whirlpool. With a whirlpool, there's always a fast enough fish, or a fast enough something, that moves so quickly it won't be pulled all the way into the center. Not so with a black hole. Within a certain distance, the black hole's power is so strong, nothing is fast enough to zip away. This is a black hole's special trait, its super pulling zone. Outside the zone, there's always the chance that something will zoom past and away, but anything inside the zone stays in the black hole's place in space forever. Nothing else in the universe is so inescapable. So a black hole is not a whirlpool. It's just sort of acts like one. There's another difference. In a whirlpool, the swirling current of water draws the fish into the center, but a black hole isn't made of water. Something else drives its power. Like a fish caught in a whirlpool, colorful glowing gas swirl toward a black hole. The darker center marks the black hole's super pulling zone. Artist representation. The pulling power of a black hole. A black hole is an extreme gravity zone. Gravity is the source of a black hole's super pull. You deal with gravity every day. You count on it to bring you back to the ground when you jump up. You depend on it when you try to catch a pop fly, knowing the ball will fall down. You expect it to be there, even if you don't think about it much. People must have always noticed that objects fall, but they didn't know what made this happen. They certainly didn't guess that falling objects had anything to do with the stars, moon, planets, and sun. But then, one man came along with some new ideas. Gravity rules. That man was Isaac Newton. In 1687, he proposed that objects fall to the ground because Earth pulls on them. But his idea reached beyond Earth. He suggested that all things pull on each other, even when they are not touching. He considered this pull a force of nature and referred to it as gravitas, which we now call gravity. And just outside a black hole's extreme gravity zone, its gravitation is still remarkable. In this artist's picture, a black hole pulls clouds of gas off nearby stars. There is the gas, and then there's Newton with the apple falling on his head. According to Newton, the force of gravity is a two-way tug between any two objects. It works with anything, any matter at all. The matter can be a tiny bit of a thing, as small as a speck of stardust. It can be a huge collection of material, as gigantic as a galaxy. It can be as rigid as a rock or as flimsy as flame. No matter what it is, if it's made of matter, then it possesses the power to pull on anything else. Newton also noted that in any situation, the strength of the pull depends on how much matter or mass is involved. When there's a lot of matter, there's a strong pull. Less matter means a weaker pull. For example, imagine a fluffy snowball and a harder packed snowball of the same size. The fluffier ball is made of less stuff. Its pull is wimpier than the pull of the densely packed ball. You can feel this difference when you hold the two snowballs in your hand. Each one presses down on your hand because of the gravitational attraction it shares with Earth. The hard-packed snowball has a stronger attraction to Earth because it's made of more material. It presses more forcefully than the fluffy one. It feels heavier. So here's a little diagram of it. It's again going to be a little hard to see, but this one has more matter and that one has less matter. And this says stronger pull, and this is the weaker pull, and then that's the Earth. So gravity works everywhere in the universe, as far as anyone can tell. It's gravity that holds the solar system together, even far away. Pluto and Neptune, as well as the outer comets, are gravitationally connected to the sun. Instead of flying off into other parts of space, they stay in our solar neighborhood. The sun's gravitational pull extends so far out because the sun has a lot of matter packed into it, about 500 times the mass of everything else in the solar system combined. Even so, our sun and solar system are just a tiny part of the universe. Most things are too far away to be swept in by the sun's gravity. Thanks again to Newton, we know that the closer things are, the harder they pull on each other, and the farther apart they are, the weaker they pull. And this is, again, a diagram of that. These ones that are closer together have a stronger pull, and these ones that are further apart have a weaker pull. This is true for all matter in the universe, including black holes. It's just that with black holes, the close-up effect is extreme. And then this is a little separate section, facts of the matter. How densely packed is the material that forms a black hole? Imagine a black hole the size of a snowball. Now compare it to a snowball made of different materials. A snowball-sized ball of fluffy snow has a mass of 37 grams, and this weighs about the same as a slice of bread. A ball of hard-packed snow is 87 grams, and it's about the weight of a small candy bar. Rock, like a piece of granite, has a mass of 287 grams and weighs about the same as a rock, of course. And a ball of plasma from the sun center is 29,000 grams, which is about the same as an 8 or 9-year-old human. And then a snowball-sized black hole has a mass of 50 octillion grams, which is the same weight as about 10 Earths. So that's kind of crazy. An extreme case of gravity. Remember that superpulling space around a black hole, the one with the strongest pull in the universe? That superpull is the close-up gravitational power of a black hole. Here in this zone, the gravity is so intense that nothing can move fast enough to fly, launch, jump, or zoom away. Around this extreme zone is a boundary called the event horizon. This boundary acts like a point of no return. Once past it, there's no going back. Only black holes have such extreme gravity zones, and only black holes have event horizons. This is what makes a black hole different from everything else. But a black hole is more than just a gravity zone, more than just empty space inside an event horizon. A black hole also includes the source of its tremendous gravitation, a massive amount of densely packed matter sitting at its center. The matter is so densely packed that it forms a single point called a singularity. Where does this matter come from? How did it get to be so densely packed? And what does it have to do with the beginning of a black hole? The answer lies in stars. So here's an illustration of a black hole with, it looks like that, and I'm going to read the things out. This is the event horizon, this outside bit of text. And then down here, this is the extreme gravity zone, kind of this part. And then the black dot in the center is the singularity. An event, what? Have you ever watched the sunset? After it sinks below the horizon, Earth blocks your view of it. Even though you know it's still out there in space, you can't see it. Any and all events on the sun remain invisible to you for as long as it is below the horizon. If the sun suddenly turned purple, you wouldn't see it happen. In a similar way, once an object enters the extreme gravity zone of a black hole, the object disappears from view. Even though nothing physically blocks our sight, once the object is beyond the boundary of the zone, we cannot see what is happening to it. Events beyond the black hole's horizon are invisible to us. Because of this visual effect, scientists name the boundary the event horizon. And then the diagram that I showed, this cross-section diagram shows the anatomy of a black hole. At the center is an extremely small, densely packed singularity, super enlarged for visibility. Surrounded by the singularity is an extreme gravity zone, colored red. The outer boundary of this zone is the event horizon. Diagram not to scale. I'll show it one more time. Yeah. So black hole beginnings. The beginning of a black hole can be the end of something else. Black holes come from stars. Every star has a beginning. When light first bursts from it, then it shines on for millions, even billions of years. But every star comes to an end, and sometimes a star's final moments are an all-out frenzy. After the dust clears, a black hole may be all that's left. Ignition. Scientists keep their eyes on this bright active spot in the sky where they can witness new star formation. Eventually, the brilliance of some stars may give way to the darkness of a black hole. False color telescope image. Looks like that. Star power. Before a star is a star, it is an enormous cloud of gases. At the start, wisps of gas and drifts of dust collect their gravity drawing them together. As more stuff gathers, its combined gravitation grows stronger. Eventually, the cloud pulls itself into a massive ball of material. Under the force of its own weight, the gigantic ball presses inward. Deep beneath the surface, the intense pressure squeezes the material like the powerful grip of a giant hand. The inner material packs together tightly. More matter mounts up on the outside, increasing the pressure on the inside. Soon the pressure in the center is so high it ignites a booming nuclear reaction. Starlight bursts from the ball of gas. Now blazing, flaring, spewing, and spouting, the new star is a fiery furnace, sparking a star. A star's fiery nuclear reaction is not really a fire. Instead, it's a dramatic melting or blending of atoms called nuclear fusion. Each atom has its own tiny center or nucleus. Surrounding each nucleus is an electrical force field. Ordinarily, this force field repels other nuclei, pushing them away. But in a star, the nuclei meld. How come? As the star material gathers, its inward pressure grows. The nuclei responds by zipping and zooming faster and faster, veering away from each other all the while. However, when the pressure gets high enough, the nuclei are going so fast, their speed overpowers their repulsion. Slamming into one another, they push through each other's force fields and fuse. As the nuclei meld, a smidgen of their matter vaporizes into energy. This creates a tremendous burst of furious noise, motion, and another byproduct, starshine. This is a lot of the nuclei colliding right there. Well, that one. And that's a star. So, in the star's center, the gas is so energized that it has become a sort of super gas called plasma. The hot plasma is in constant motion. It expands like hot air inside a balloon and pushes outward from the center. Meanwhile, the crushing weight of the star material continues to press inward. In goes the outer material and out goes the inner. The plasma rolls and churns like a hyper hurricane of heat, light, sound, and motion. The star ball holds together in this perfectly balanced commotion for millions or billions of years, until the star's nuclear furnace runs out of fuel. The reaction suddenly ceases. When that happens, look out! The end of the star is near. Like other stars, the sun is a blazing ball of activity. As the brightest and hottest material rolls and swirls, darker, less hot material sinks toward the center. The flare in the upper ridge is a tremendous whip of plasma lashing out into space. So that's some of the plasma lashing out into space, and that's our sun. Out of fuel, out of time. Some stars go out in a blaze of glory. Once the nuclear reactions stop, the star center begins to cool. The plasma slows down, its outward push growing weak. The balance is broken. The plasma collapses in on itself. In one giant whoosh, the center of the star compresses. It caves in, growing denser and tighter than ever. Crash! This core material bumps hard against itself. Boom! The material rebounds like an ocean wave slamming against a rock cliff. It pushes on the star's outer gases, which flow outward in giant surges of heat and light. As the star's material rushes outwards, the star grows and grows until it's a supernova or superstar. What happens next? Possibly a black hole forms, possibly not. In this artist's illustration, a massive star comes to a spectacular end. Its gases rebounding from the dense center and surging outward in a burst of light, heat, and motion. Looks like that. It all depends on the original mass of the star. If the star was about 25 to 40 times the size of our sun, then what's left of the star center goes into a sudden collapse called fallback. Once again, the star's stuff plunges inward until under its own weight. In, it pulls. Tighter and tighter, the material contracts, crunching in so fast and so hard that it's destroyed. Even its atoms are utterly demolished. All the matter that once filled the center of the star shrinks down to a single tiny point of extremely dense mass. It has no recognizable parts, but it does have one feature that makes it unique. It has a pull of gravity so strong that it can outpull anything else in the universe. Nothing can outtug it. No army of tow trucks, no convoy of supersized earth haulers, no fleet of giant rock engines, not all of them combined. Do you recognize this pull? It's the pull of a black hole. The star, a big, brilliant ball of light, has turned into a dark place of enormous gravitation. A black hole has formed. So in 1987, a distant star appeared as a pinpoint in the before picture before bursting out as a brilliant supernova in the after shot. You can see the tiny one and then bursting out before and after. What happens to the other stars? All stars run out of fuel, but not all stars end up as black holes. Which stars form what? If the star is up to 9 times the mass of the sun, such a low-mass star never becomes a supernova. Instead, its inner core turns into a small whitish ball of cooling material called a white dwarf. Every day you see a lightweight star that is destined to become a white dwarf. The sun. And then this is an artist representation. And then, if the star is 9 to 25 times the mass of the sun, the star is not quite heavy enough to form a black hole. It goes through a supernova, but when it falls back in on itself, its gravity isn't strong enough to crunch the material into a singularity. Instead, it forms another type of star, called a neutron star. Like other stars, neutron stars are ball-shaped and emit light, but they're much denser. Only black holes have a greater density. This is another artist representation. If the star is 25 to 40 times the mass of the sun, the gases blast out as the star goes supernova. Then the remaining material collapses inward, forming a black hole by fallback. Here's another artist representation. And then, if the star is over 40 times the mass of the sun, when this type of ultramassive star runs out of fuel, it goes through an initial whoosh of collapse. However, because its enormous mass generates such tremendous gravitation, there's no crash of a rebound or a boom that blasts gas into the supernova. Instead, the matter just keeps on whooshing inward, directly forming a black hole. And then there's the artist representation. The blackness of a black hole. A black hole is black because no light comes from it. A black hole is nothing to look at, literally. If you could somehow take a close-up picture of a black hole, it wouldn't be one for the scrapbook. It would just be blank and black. The blackness of a black hole is peculiar. Although there's plenty of light within a black hole, you can't see it from the outside. Yet there's no wall physically blocking the light or bouncing it back in. Instead, gravity keeps the light contained. This artist's illustration helps us imagine the utter darkness of a black hole from which no light escapes. Moving light, the movie. You may not think about it much, but light moves. It travels from one place to another, and that takes time. But not much time. When light travels, it moves fast. Our eyes and brain can't keep up, but you can slow down light to see what's going on. If you run what's called a thought experiment. In a thought experiment, you use your imagination to conjure up an experiment you couldn't do in real life, at least not easily. Then you run things through in your mind and see what might happen. For this thought experiment, you'll need to imagine a slow-motion movie of light. It's okay to imagine popcorn, too. It's a misty night. In the darkness, a pinpoint of light becomes visible. Someone has turned on a flashlight. The pinpoint grows to the size of a bulb. Because this is slow motion, only the bulb is bright. Nothing else lights up yet. Now, the light begins to spread outward from the bulb. It fills a bigger and bigger space. As the light moves forward, it strikes little fog droplets, the ground, a sneaker, a tree, a cat. After each collision, some light bounces off. It is redirected. Some of it reaches a person's eyes. Only then can the light trigger the person's eyes and brain. In slow, stretched out speech, the person says, "Look, a cat." When the action action slowed down, you're able to notice the time it takes for the light to move outward from the bulb to the person's eyes. This was a short trip for the light. There wasn't much going on. On longer trips, more might happen. The light might encounter places of extra intense gravity. Then things would be more interesting. Time for a sequel. This time, the action is set in outer space. Measuring distances with light. How fast can you run in a second? 6 feet? Couple of meters? In that same second, light would travel more than 900 million feet, about 300 million meters. That's almost from Earth to the moon. This length can be called a light second because it is the distance light travels in a second. A kid second would be those 6 feet you just sprinted. A light second might seem like a big distance, but compared to the universe, it's puny. Astronomers need much bigger units of length to describe those stretches of space between stars. One unit they use is the light year, which is the distance that light can travel through space in a single year. A light year is about 31 quadrillion feet, or about 6 trillion miles, over 9.5 trillion kilometers. Compare this to a kid year, about 26,000 miles, or a little under 42,000 kilometers, though so far no kid is reported sprinting nonstop for an entire year. So, the sequel, Bending Light. In Moving Light 2, light is on the go again. This time, in a slow-motion trek through the universe, you track its path as it moves outward from a star, instead of a flashlight. Some of it bounces off asteroids, gases, and dust in its way, just as it reflected off the droplets of fog on Earth. However, as the light passes extra massive objects, big stars, huge planets, whole galaxies, something else happens. The light changes direction. Pulled by the object's gravity, it veers off its straight-line course. The more intense the gravity, the more the light's path bends. Just outside the event horizon of a black hole, light's energy keeps it zipping along, like that fish swimming along the outer edge of a whirlpool. Although the black hole's gravity changes the light's path, the light doesn't swerve into the black hole, which is illustrated here. However, if light does cross the event horizon, the greater intensity of gravity makes the light curve inward. As the light continues traveling in its new direction, it gets even closer to the center of the black hole, where gravity is even stronger. The closer the light gets to the center, the more gravity is redirected inwards. And that's shown right here like this. In this way, the light traces an inward spiral. Because the light never turns out again, it can't reach our eyes or the telescope. This utter absence of outward-bound light is why black holes are black. From the outside, a black hole is invisible. But if it's invisible, then how can we know it's there? How can we find it, especially if it's quadrillions or more miles away? Bending starlight. What's the evidence? Can gravity really change the path of light? In 1919, the scientist Arthur S. Eddington led a team to investigate this question. The team photographed the same stars at different times, once during the night and once during the day when the starlight passed very close by the sun on its way to Earth. If gravity could affect light, the sun's powerful gravitation would bend the starlight, changing its path. This change would create the illusion that during the day the stars move slightly from their nighttime positions. After carefully comparing the photos, the scientists announced the results. The stars seem to have moved. This was the first evidence that gravity does affect light. So that's this diagram right here. So this is the apparent position of the star, this one, and then this is the actual position of the star. So the path of light is bent by the sun's gravity, and we're used to light coming to us in straight paths. When light from a star is bent on the way to Earth, the starlight appears to come from a different spot than it actually is. And this diagram's also not to scale. So, whoop, to us, the observer on Earth. Mission Impossible, Seeking the Invisible. A black hole is like a hiding place in space, with footprints leading to it. There's more to invisibility than what doesn't meet the eye. All sorts of things are invisible to us, for different reasons. Some, like atoms, are too tiny to see. Others, like a black cat on a dark night, aren't lit brightly enough. Certain things are invisible to us because our eyes just can't sense them. You don't see beams of infrared light shooting across the room from your remote control to the TV, for example, or radio waves streaming off everyone's cell phone. Then there's the invisibility caused by a black hole. No matter how hard you look, you can't see the black hole itself. There's nothing at all coming from it. No light, no other forms of energy, and no matter. We can detect only what's around it, never anything inside. But there are clues that hint at the presence of a black hole. Scientists use these clues to track them, the way you can follow footprints right up to someone's hiding place. So thanks to telescopes that translate invisible energy into color-coded pictures, we can see red jets of invisible radio energy fountaining from the area of a black hole. On the trail. One of the best black hole clues is the X-ray energy. As matter approaches an event horizon, its atoms shine with invisible X-rays. Although our eyes can't see the X-rays, we can make detectors that respond to their tremendous energy. X-ray catching telescopes make pictures of otherwise invisible X-rays. The pictures reveal that certain areas in outer space are emitting intense X-rays. Each bright location points out where something extraordinary is going on. It is a hint that a black hole might be there. Acting on the hint, scientists search the X-rays for patterns that most likely signal black holes. One pattern is an X-ray ring that seems to surround nothing. The nothing part might be a black hole. If so, the ring is energy released by the superheated matter spiraling just outside the event horizon. So X-ray rings in space can clue scientists into a possible black hole. This is the artist interpretation. So a science friction story. X-rays can mark the spot of a black hole, but what generates them? Some exotic black hole feature? Nope. The X-rays are generated by plain old friction. Friction is what makes your hands warm when you rub them together really fast, or what makes rubber burn when a car screeches to a halt, tires skidding on the road. In the same way, material swirling in toward a black hole skids past other matter and heats up. As you might expect, near a black hole, the friction is extreme. The material heats up so much that it begins to glow in invisible, super powerful X-rays. So, scientists also seek patterns in the intensity of the X-rays. Just as you rely on the rise and fall of a melody's tune and the volume to recognize a particular song, scientists look for the unique pattern in the rise and fall of the X-rays to identify a black hole. Telltale signs of strong gravity may also point to a black hole. One spectacular gravity footprint appears as smudged multiple images of galaxies. Such images can form when the light from faraway galaxies passes near a black hole but does not cross the event horizon. Sometimes the galactic light splits up and bends around the black hole. Some light goes left and some goes right. Some goes up, some goes down. The beams of split up light make it around the black hole, but may not come back together again. Like reflections in a kaleidoscope, they create multiple images of the galaxy around the black hole. So the circled blue smears in the picture are multiple images of just one distant galaxy. On its way to the telescope, the light from the galaxy passed a group of other galaxies. Their combined gravitation was strong enough to split the blue galaxy's light. A black hole can create the same kind of special effect called gravitational lensing. So again, it's probably going to be a little hard to see, but there's some of those blue circled galaxies. And there's another one, I think, right there. A star's motion can also reveal a black hole. Imagine two ice skaters gripping hands and whirling around each other. What if one of the ice skaters were somehow invisible? His partner's whirling motion would give them away. Similarly, if a visible star whirls around the dark area in space, its movement suggests an invisible partner. The more intense the gravity of the invisible partner, the faster the visible star will swing around it. If the visible star cuts a fast enough orbit, then chances are good that only the strongest of gravity sources, a black hole, is there. So, one telltale sign of a black hole is the incredible speed at which a visible star whips around its invisible companion. The star GRO J165540, shown in this artist's image, zooms around its black hole partner every 2.6 days. Mistaken identities? But there's a catch. Black holes aren't the only thing that can cause X-ray rings, multiple galaxy images, and whirling stars. When astronomers discover one of these clues, they have to be careful not to jump to conclusions. And there's another challenge. Out in the universe, finding and interpreting X-ray signals, motion patterns, and other evidence can be tricky. Reality complicates the search. It's hard to get a detailed image even with our best telescopes. Also, between a black hole and us is a lot of space, with galaxies, stardust, gases, and more. The clues are like footprints in a crowded forest. Maybe you can see them and can follow them, but maybe paw prints, branches, leaves, and shadows muddle the picture. It takes a while for astronomers to sort through these complications. Once they spy a black hole candidate, they get to work on the evidence. How does the candidate compare to what they expect from a black hole? Are there other ways to explain what they see? If the evidence lines up just so, the astronomers move from being pretty sure to almost positive they've found a black hole. That's how science can work, but sometimes there are twists. And then this little blurb down here, this little thought bubble says, the old scientific saying, if it looks like a duck and quacks like a duck, then we can safely state it is likely to have its identity as a duck confirmed at some point in the future pending additional evidence. And the duck says quack. Supersized surprises. A black hole is sometimes where you least expect it. One unexpected twist came as a black hole discovery that scientists never dreamed of. The story begins with a mystery from nearly 100 years ago. For decades, it seemed to have nothing to do with black holes. The story ends with a really big surprise. And this is some constellations right there. Star patterns light up the night and remind us of ancient myths. In the 1900s, scientists discovered that some of these constellations held tantalizing clues to a bigger story. Radio mysteries. In the 1930s, a telephone company engineer named Karl Jansky was trying to track down the cause of hissing static in phone lines when he discovered something strange. Radio energy from outer space was interfering with the phone signals. After learning about Jansky's discovery, a radio engineer named Grote Reber decided to investigate. Reber had just one little problem. To explore the radio energy, he needed a radio telescope, a telescope that could detect invisible radio energy, but there was no such thing at the time, so he invented one. He built it in his backyard in Wheaton, Illinois. Late into the night, Reber probed the sky with his new telescope, using it to locate the source of the mysterious radio energy. Reber mapped these signals from the sky and shared his findings. Astronomers followed up with new investigations and soon began reporting more signals. Over time, with better radio telescopes, they found that some radio sources appear as paired patches, one on either side of a tiny dot. They called these sources radio galaxies. They also discovered other, more star-like sources, intense dots of radio energy without patches. How strange. What could these quasars, short for quasi-stellar radio sources, be? Were they related to the radio galaxies? So, in 1937, Reber built this radio telescope from wood and sheet metal. His backyard wonder launched the study of invisible light energy from space. So this is a picture of his invention. Reber found that some of the strongest radio signals from space came from the direction of familiar constellations, such as Sagittarius, the Archer, Cygnus, the Swan, and Cassiopeia, the seated queen, which look like these. It's the Archer, and this is that's the Swan. Actually, that's the Swan. That's the Archer, and this is the Queen, I believe. So finally, in the early 1980s, improved images revealed a stunning new picture. The radio's galaxy patches were actually the ends of colossal streamers of energy, each one stretching hundreds of thousands of light years from the center. Something powerful had to be driving these gushing fountains of energy. And the quasars? They turned out to be far, far away, yet somehow creating radio impulses strong enough to reach Earth. No star could do this. In fact, every quasar and radio galaxy dot turned out to be energy from the center of an entire galaxy. Astronomers found stars careening around these centers, zooming at previously unheard of speeds in their orbits. The motion was like an accelerating ice skater pulled around their partner in a tight twirl, or like a fish caught in a super strong whirlpool. Something extreme had to be in the middle of each of those galaxies. In this false color telescope image, lobes of radio energy shoot away from the center of the radio galaxy, Cygnus A. Each enormous lobe is about 300,000 light years long. You might be able to guess what this was, but for scientists, the best answer came as a shock. In 1994, telescopic evidence confirmed the amazing cause, a supermassive black hole, with a mass not of one imploded star, not of two, but of millions, maybe even billions. Imagine the excitement. Scientists had discovered a new, entirely unexpected class of black holes when they weren't even looking for one. It was like playing hide and seek and tripping over a whole group of people you never knew were in the game. As it turns out, supermassive black holes are probably at the heart of almost all galaxies, including our own. As this artist's illustration shows, matter colliding near a supermassive black hole can kick up a ruckus of energy. Such energy footprints help scientists in their search for black holes. Field Guide to Black Holes. Discoveries of black holes exploded in the late 1900s and early 2000s. What scientists found reads like a cast of characters for a mixed-up fairy tale. First, they discovered the small baby bear black holes, then the giant papas. But where were the medium mama bear black holes? It just didn't make sense that there would be smalls and larges, but no mediums. Astronomers began the search and found them. There's just one size that still hasn't been found, even though it's been predicted. The tiniest of all, the Tom Thumbs of the black hole world, have yet to be discovered, if they even exist. Size in order of discovery. So here's the illustration with all the porridge. But size in order of discovery, there's the small, what the pros call it, stellar mass black hole. Has the same amount of mass as 3 to 10 suns. Forms when a large enough star ends, either in a supernova or by directly collapsing when it runs out of fuel. Extra, extra, extra large supermassive black holes has the same amount of mass as millions to billions of suns. And it forms when stars, galaxies, and or black holes collide, huge gas clouds collapse, a smaller black hole grows as matter falls in or over a long time. Nobody's sure. Medium. What the pros call it, intermediate black hole, has the same amount of mass as 100 to 10,000 suns. Stars and forms when stars merge and then collapse. People are still mulling this over. And then extra, extra small, about the size of an atom or smaller. Micro, mini, or primordial black holes, or what the pros call it, and it has the same amount of mass as Mount Everest. And it forms when, well, there's no evidence yet that these tiny black holes exist. If they do, they may have formed when the universe began because of tiny imbalances of matter and energy. Supermassive startups. We live in the Milky Way galaxy, far out on the edge of one of its spiraling arms, which is, in the illustration, we are here. Our part of the galaxy is relatively calm, but in the center is a supermassive black hole, a compaction of 3 million suns worth of matter. This black hole is pretty mellow, as supermassive black holes go. Because its X-ray signal is relatively weak, astronomers didn't find it for a long time. They still don't know how it's formed. In fact, scientists are still puzzling over how any supermassive black holes get started. Could a single supernova lead to one? Probably not. Even the biggest stars are much too puny to do the trick. To create a supermassive black hole, a star would have to start out millions of times the mass of the sun. Astronomers think this is unlikely, so they have come up with other ideas. One idea has to do with crashing stars. Near the center of a galaxy, stars are crammed relatively close together. As gravity swings them around each other, high-speed crashes are inevitable. Gravity can also cause entire galaxies to swerve together in intergalactic collisions. When the huge amount of matter in colliding stars and galaxies compacts forcefully, it might form a mid-sized or intermediate black hole. With enough of this going on, several black holes might form and then pull together, morphing into one. Nearby stars might also spiral into these growing black holes, adding to the total mass. Over time, all this piling up might lead to a supermassive black hole. Radio galaxies, quasars, supermassive black holes. In less than 100 years, we've made many discoveries about black holes. The theory works and the evidence is good. The conclusion seems sound. But still, all of this evidence is like guessing what's inside a gift box, but not being able to open it. If you could, wouldn't you want to peek inside the package and see for yourself? Wouldn't you want to visit the black hole? And so our galaxy's central black hole is calm compared to others, but it still packs a wallop. Zooming in on the center of the Milky Way, we see a white hot spot that reveals the intensity of energetic activity surrounding a supermassive black hole. That's this picture. Whoops, wow. It's a little tough to see. Maybe better? I don't know. But yeah. And then deep in the center of the galaxy, NGC 6240, two unseen supermassive black holes are merging in a slow motion collision. The crash began 30 million years ago and may continue for another 100 million years or more. The collision creates a bright splash of X-ray energy captured here in false color. That's this one. So tomorrow's news. It seems that every time you turn around, astronomers are discovering something new about space. But this wasn't always the case, especially with black holes. It took several decades to go from thinking black holes could be possible to actually tracking one down. Compare that to what's been happening more recently. Within the past decade or so, scientists confirmed that supermassive black holes exist and figured out they must be at the center of most galaxies. Astronomers found intermediate black holes and discovered the first solo stellar mass black holes, ones without visible partner stars. And they have tracked matter falling into a distant black hole and determined just how a black hole propels its superenergetic jets. The fact is, you've been alive during some of the most exciting times in black hole astronomy. Just imagine what scientists may discover by the time you're 20. And what's really cool is this book was written before they took the first picture of a black hole. So now they actually have a picture of an actual black hole, or at least what you can see of all the matter surrounding it. But sorry, little interjection there. All right, meet the neighbors and then some, getting to know a few black holes. Thousands of objects either seem likely to be black holes or have reached almost positive confirmation as black holes. Which ones are closest, smallest, biggest? Here are some black hole highlights. Sagittarius A. Type, supermassive. Importance, the black hole at the center of our galaxy. Location, the center of the Milky Way galaxy, which is 27,000 light years away, in the constellation Sagittarius. Cool fact, today we know that Sagittarius A star is one of the mysterious radio sources that Grote Reber discovered with his homemade telescope. It is 4 million times the mass of the sun. So this is the Sagittarius A star. All right, NGC 5128, also known as Centaurus A. Type, supermassive. Importance, the black hole in the center of our nearest active galaxy. Location, about 14 million light years away in the constellation Centaurus. Cool fact, at 200 million times the mass of the sun, this black hole is far more massive than Sagittarius A star. V4641 Sagittarius, also known as V4641 SGR. Type, stellar mass. Importance, one of the closest known black holes to Earth. Location, 1,600 light years away in the constellation Sagittarius. Cool fact, V4641 Sagittarius I is actually a binary system with one visible star and one black hole circling each other. NGC 4486, also known as Virgo A, type, supermassive. Importance, one of the biggest of the biggest. Location, 50 million light years away in the constellation Virgo. Cool fact, this black hole is really huge. The distance from one side of its event horizon to the other is about the same distance across as Pluto's orbit. It has an estimated mass of 3 billion times that of the sun. Cygnus X1, type, stellar mass. Importance, one of the smallest known black holes, also one of the first ever black hole candidates. Location, about 6,000 to 8,000 light years away in the heart of the constellation Cygnus. Cool fact, this black hole is so small that it would take less than an hour to drive the distance across it. Oops. And here's the artist representation. And that's all of them. Close encounters of the imaginary kind. A black hole is a destination for your imagination. Unfortunately, for the curious traveler, actually visiting a black hole in the near future is downright impossible. Even the nearest black holes are too far away. For example, one of Earth's closest black hole neighbors is about 1,600 light years away. That's about 9 quadrillion miles or 14 quadrillion kilometers. No spacecraft is going to get you to a black hole and back by dinner time, even if you live to be 100 and only want dinner on your last day. Luckily, you can visit a black hole with your imagination. Fueled by facts, you can blast off to a black hole or two and find out what might happen when you arrive. So what might happen to a spaceship approaching a black hole? This is the artist representation. The closest black hole to Earth. If you were to aim a powerful enough flashlight at the moon right now, the light would reach it in a little more than a second, maybe before you got to the end of this sentence. And how long would it take for light to reach our nearest known black hole neighbor called V4641, Sagittarii? 50 billion seconds. If you aim your flashlight in its direction towards the constellation Sagittarius, light would arrive there sometime around the year 3600. A whole variety of places to visit. As you take off, remember, predicting the exact details of your journey is tricky. After all, no one has ever visited a black hole, and we can't send a probe in to take a peek and send the information back to us. Not even sneak previews can escape from a black hole. However, scientists have some guesses about what would happen based on what they know about gravity in black holes. A helpful rule of thumb is that close to the center of any black hole, every inch matters. Just a short distance can make an enormous difference in the strength of the black hole's gravitational effects. The particulars of your adventure also depend on the type of black hole you visit. What size is it? Is it lumpy or smooth? Maybe it's a spinner? Spinners, lumpies, and smoothies. When it comes to black hole, matter really matters. After all, if it weren't for all the matter crunched into a tiny space, an extreme gravity zone could never form. But it's not just how much matter and how small a space that makes the difference. How a star's matter collapses also affects the black holes that form. If the star was spinning before the collapse, then the black hole will spin too. If the collapse is perfectly symmetrical, a smooth black hole forms. On the other hand, even a slightly lopsided collapse leads to a lumpy black hole with erratic gravitational effects. The gravity might be strong in some places and weak in others, and pull in different directions. However, a lumpy hole won't stay lumpy for long, because its own gravity will work to smooth it out. Beyond your brainy blast-off journey to a black hole. Suppose you were to visit a perfectly symmetrical, smallish, non-spinning black hole. What would happen? Right away, you would need a new nickname, something like Stretch or the Spaghetti Kid. The pull from the black hole would force your body into a long, skinny, stringy shape. If you were going in feet first, your feet would stretch out the most. For a moment, they might look like droopy, wet socks. Not that you would notice any of this. By the time your toes could register ouch in your brain would not be working. This is the one time when stretching your mind might be a bad idea. What if the black hole were lumpy? Instead of getting a nice, smooth stretch, you'd be pushed and pulled in changing directions, like a human dough in a wrestling match with a pretzel maker. The pretzel maker wins. A kid visiting a black hole might be stretched out like spaghetti. Scientists call this phenomenon spaghettification, or the noodle effect, which are pretty funny names. So much for experiencing a smallish black hole. You'd have no time for sightseeing. A visit to a bigger black hole could be more interesting. It might take a while for the major effects to kick in. As you drifted in from the event horizon toward the singularity at the center, you might get a chance to look around. What might you see? Even before you crossed the event horizon, things would start to look strange. The black hole would bend the light from all around and focus it in a miniature picture. Instead of seeing a sky full of stars, you'd see a tiny image of the black hole's surroundings, focused smack dab in the middle of the blackness overhead. Even stars on the opposite side of the black hole would be visible above you. After you crossed the event horizon, the warped sky image would distort even more. Now the light from everything outside the black hole would form a ring above you, like a halo overhead. Your sky would appear dark except for that bright circle, a ribbon of light that would get skinnier and skinnier as you continue to zoom inward. You might want to tell the folks back home about this. Ah well, too bad. Once across the event horizon, you wouldn't be able to get back out. Any blog or vlogs, emails or phone calls, snail mail, smoke signals, messages in a bottle, or signal flares to spread the news. It would be as if you were stuck in a one-way, sight-proof, sound-proof bubble, sealed away from the rest of the universe. But there's no sense letting that tear you up. In a few hours, gravity will do the job instead. Maybe you'd better turn that imagination of yours around and head back to Earth. That's the thing about thought experiments. They let you experience the impossible and still get home in time for dinner. Well, usually. One of the best ever thought experiments missed more than a meal or two while on his mental adventures. I'm often so engrossed in my work that I forget to eat lunch, he wrote in a letter to his 11-year-old son just days before he unveiled one of his biggest ideas to a group of scientists. And what an engrossing, even bizarre idea it was. It took scientists on an incredible journey, a fantastic voyage through space and time, and eventually led to black holes. We'll get to that in a second, but first, what you would see far away from a black hole. And it's just that. Approaching the event horizon. And then after crossing the event horizon, and that's when you see kind of the ring and halo. So, ultimate FX. Careening towards a singularity, you might have a colorful experience, if only for a blink of an eye. Picture the colors in a rainbow, and the invisible light on either side, such as low-level infrared energy beyond red and high-energy X-rays beyond blue. Got it? Now forget it. Viewed from in and near a black hole, colors can undergo some shifty effects, sliding from the red side of the rainbow towards the blue. Yellow, green, and blue stars disappear until you spot them with your X-ray detector. Meanwhile, the new stars wink into view, balls of gas that glow in shifted infrared. Why? Light is distorted as it passes between places with different gravitation. The greater the difference, the greater the distortion. A black hole's extreme gravity intensifies this effect to the max. Now try this tasty thought experiment. Say some friends far outside the black hole decide to send you a snack. If they launch a red apple your way, it's invisible to you at first. But keep your eyes peeled. Eventually, the apple shifts from invisible to blue, then to green, yellow, orange, and finally red, as it passes through the gravitational zones that are closer and closer to the same strength as yours. Quick, grab that apple before it disappears. Remember, once it whizzes past you, all its light continues in one direction, toward the center of the black hole, and you won't see it anymore. And just remember, predictions like these are iffy. They're based on what scientists know about light and gravity, and they might be right if the known laws of physics don't break down past the event horizon. So here's the little diagram of how that works with all the colors. So what you normally would see is yellow, and then it shifts to green, and then eventually what you see from the black hole, nothing. So the color of the star shifts as you approach the extreme gravity zone of a black hole. And this diagram is not to scale. So turning the universe upside down. A black hole is part of a strange new universe. The scientist who forgot to eat his lunch was busy cooking up a whole new way of thinking about gravity. He was a radical smarty pants, somebody with a wild imagination, someone whose brain could surprise even himself. Albert Einstein didn't mean to turn the universe upside down on everyone. He didn't plan on leading others to discover black holes. At first, all he set out to do was think about motion, along with a few other related ideas. But almost before he knew it, he had suddenly made our dependable old universe seem strange and new. And this is the picture. Just imagine being on an alien world and catching this old view of a black hole in the sky. Imagination has always helped open the door to new ideas in science. In fact, imagination led scientists to the idea of black holes. And there's the sandwich as well. Einstein's spacey ideas. Before Einstein, everyone pretty much thought of space as a sort of blank nothingness that separates objects like planets, solar systems, stars, and galaxies. This nothingness of space was a humongous, rigid background with all of the matter in the universe arranged on it like pieces on a game board. Newton's force of gravity ruled this game, pulling things closer together and making them move against the spacey backdrop of nothingness. But Einstein had his own ideas. What if this background wasn't rigid? What if it wasn't nothingness? What if it didn't stay the same all the time? What if instead space itself was something that changes and even reacts to mass and matter? Thanks to Einstein, we can imagine space as a blanket that stretches in response to every object's mass. A more massive object, such as the Earth, makes a deeper depression, and a less massive object, such as the Moon, makes a smaller depression. That's illustrated right here, where it bends underneath. So, in this way of thinking, the background acted more like a flexible mat or a stretchy knit blanket. This new blanket-like idea of space meant space could stretch, crunch up, bend, and warp. Moving objects would follow the curves of the blanket, moving along the surface through flat sections, as well as distorted ones. This new idea about space changed the way scientists think about gravity. Speaking of gravity, Newtonese and Einsteinese. Most of the time, gravity seems to work the way Newton described it. Newton's rule explains a lot, from falling apples to most planets' orbits, but this law doesn't work perfectly. In high gravity zones, Newton's ideas don't jibe with what scientists observe. So, for example, Mercury's orbit up close to the Sun has a blip in it that Newton's laws can't explain. Glitches like this one were the reason Einstein worked so hard at coming up with a new explanation. He wanted to account for everything. His ideas about curving space may sound bizarre, but they work. They took care of the gaps in Newton's theory and explained Mercury's orbit. They led scientists to predict shifting starlight and black holes. All of this is powerful evidence that Einstein was onto something. However, in day-to-day experiences, the strangeness of Einstein's ideas don't help us, and Newton's notions do just fine. In everyday life, when gravity isn't especially intense, Newton's and Einstein's ways of thinking lead to similar results. The two explanations work like different languages that express the same thing. Is an apple red, English, or rojo, Spanish? It's okay to use either description. So we still use Newton's laws. Even scientists do, much of the time. Sure, it's more exact to be Einsteinian and think of gravity as matter's effect on space, but it's all right to take a Newtonian shortcut and imagine gravity as a pull. Gravity, a real mind and space bender. In Einstein's way of thinking, what we see as gravitational attraction between two objects isn't really the effect of those objects pulling on each other. Instead, gravity is the effect that matter has on space itself. Any material in space causes a distortion of some sort. A small concentration of matter results in a tiny dimple. A higher concentration makes a deeper dent. Each indentation is the gravity zone around the object. Near the object, the distortion is greatest. The stretchy threads of the space fabric are bent by the effect of mass on space. Farther and farther away, this effect is smaller and smaller, and so the threads are straighter and straighter. A peanut would form a shallow dimple. If you could squash two peanuts together so they took up the same space as one, the dent would be slightly deeper. The deeper the dent, the steeper the gravity zone. It would take more energy for things to get out of the deeper dent. From Einstein's gravity to black holes. Einstein's idea of gravity has big consequences. It helped explain some observations that Newton's ideas didn't account for. It also opened our minds to the amazing new possibilities. For example, taking his cue from Einstein's idea that space bends, scientist Carl Schwarzschild began to think about what would happen if a place in space were extremely distorted. His answer: light would follow the hyperbent space, never to turn away from it. This was the first prediction of a black hole. At first, some scientists, including Einstein, rejected Schwarzschild's ideas. Others were intrigued and began searching the skies for real black holes. Just decades later, they found the first of them. It just goes to show, sometimes, as Einstein once said, imagination is more important than knowledge. So the dense singularity at a black hole center would be an extremely tiny but extremely heavy object placed on the blanket. Picture the supernova leftovers, the material that originally forms a black hole, as a peanut with all of the elephants in the world stuffed into it. Imagine placing that tremendously dense elephant-stuffed peanut on a huge blanket. The blanket stretches and stretches, pulling out of shape. It forms not a shallow dimple in the blanket, but a steep well. A steep well that's really a lot like, and so an elephant-packed peanut would be small and magnificently massive. It would cause the deep dent in the fabric of space. And that looks like this. It's hard to see, but it's stretching down like that. So the steep well is really a lot like a hole. So even though a black hole is not a hole, at least not the kind you can poke your finger through or dig in the ground, a black hole is not exactly not a hole either. Is it? Glowing gas and dust whirl around in a black hole. As they follow the dramatic curve in the fabric of space, they spiral along the steep gravity well that leads to the dense singularity at the center of the black hole. That's this representation. That is, a black hole is not a hole. I hope you enjoyed. Thank you.